Okay, so hello guys. Today we're going to be tackling an optimization question. Okay guys, now that you've been presented with the problem, I want you guys to think of a difficulty that could be faced by a student when trying to solve this problem. Does anyone know?
Oh, Miss, I know an answer. I know a difficulty.
Lauren, go ahead.
Well, I think that maybe a difficulty would be setting up the problem in terms of one variable because we have to use two equations here.
Oh, that is perfect. Yes.
So the first thing we're going to do is draw a diagram for this problem. We are given a rectangle whose perimeter needs to be as small as possible. So now we're going to label the length and width. So I'm going to make the length as the x value and the width as the y value. So now we can see that we have a perimeter equation and an area equation, and they both have the variables x and y. So now we can solve the area equation in terms of either variable. It doesn't matter. This time we're going to pick y to create a constraint. So you're going to say that y equals 1,000 over x.
Alright guys, now that we have had the perimeter equation in one variable of x, and if you remember, that was strategy 3, and which tends to be actually the most difficult for most students. So good job, Lauren. And now what we're going to go ahead and do is find the derivative of this.
Okay, so now that we found our first derivative, does anyone know a test that we could use in order to take the next step in finding the minimum perimeter?
Oh, that's easy. We just find critical points by setting it to 0. Duh.
Okay, so what test is that?
Oh, that's simple. It's the first derivative test.
Exactly. Thank you, Belissa. So now that you've had time to set your derivative equal to 0 in order to solve for the critical points, we have the critical points of x equals the square root of 1,000 and x equals 0. In this case, since we're measuring the dimensions in length and width, we can't have a dimension of width of 0.
Now that we've found our critical point, which is x is equals to the square root of 1,000, we actually have to figure out whether at this critical point a minimum really does occur. So the way that I like to go about this is to draw a simple number line, and where we put the square root of 1,000 in the middle. And so what we're going to do is we're going to test for values less than the square root of 1,000, then we're going to plug it into the derivative equation, and then we're also going to test values greater than the square root of 1,000. And
we can see that when we plug it into the derivative, that at 1, just a number below square root of 1,000, the function is decreasing. Another number above the square root of 1,000, we see that the function is increasing.
And just to note, we know that it's decreasing because we got a negative value, and we know that it's increasing above the square root of 1,000 because we got a positive value.
So in this case, because the function is decreasing from the left and increasing from the right of the critical point, we have a minimum.
Okay guys, so now that we know that a minimum actually does occur at that critical point, which is x is equals to the square root of 1,000, we can find y. Now, where do we actually plug y into?
Well, we actually plug y into the constraint expression that we made earlier. So 1,000 over x equals y. So just plug in our critical point of the square root of 1,000 right here, so we can get our x and y dimensions, which is the length and the width. And then you're done.
Oh, but Lauren, just one more thing. Don't hold up right there. We still have to find our perimeter. And thank you guys so much for going through this journey with us and figuring out how to do this optimization question.
We hope that our strategies help you solve optimization problems in the future.